Hi, guys. So there's an SI session tonight, but it's not scheduled like usual. It starts at 9 instead of 8:30. So if you want to come do chemistry, you should show up to Guilford 323 at 9 because that's what all the cool kids are doing.
And also tomorrow I have my normal session, but you can notice the time has also changed for that. So it's from 4 to 5:15. I have to cut off 15 minutes because I have to be in Twing at 5:30. So sorry about that. And then Wednesday we'll have our normal session from 7:30 to 9:30, the exam review. So notice the 2 time changes for today and tomorrow. And then Wednesday will be the normal time, normal place, 2 hours exam review.
Thinking right at the same time? Not me, I'm never distracting. Mustafa, what's up? Everything's got to be in by the last Monday of the semester. I'll accept no bonus things after the Monday, April 29th. I'm sorry? Emma, come on. I don't have that form posted, so just send me an email with the reflection. So, yes. The reflection, remember, is just what you got out of it. It's not a book report. I don't want you to tell me this is what the seminar was about, this is what it was like sitting out there, this is what I observed while I was sitting. But it's really, what did it mean to you? It's your reflecting on whatever it is that you participated in. Come to that. Yes. If you just know, the people who are getting a bonus are those who did a 2-hour shift at the wall. No, you just can't stop and look at the wall to get a bonus. You did a 2-hour shift at the wall. And I know some of you did an hour and said, I need to leave. And some of you came back and did the second hour, but several of you didn't. The deal was a 2-hour shift at the wall. So if you're one of those persons who did an hour and then walked away, I'd appreciate it if you did not submit a reflection. That was not the deal. So bonus opportunities. I'll post these to Blackboard. I spent the weekend recovering files off my computer, so I now have them. Reason I had to do that is I was missing the grades from the other class, so I had to find that file. Opportunities between now and the end of the semester, any 2 seminar that you can find and write a reflection on them. Any arts event, movies, theater, or theater live productions of musical events, theater, if anybody went to Tartuffe this weekend. Bonus, remember, I'm encouraging you to write the final exam. But there needs to be enough questions for me to pick from them, so post them to the discussion board. If I use it, it's 2 points. 1 point if you submit one, and I'll send you an acknowledgement to that effect, but 2 points if I use it. I thought there was a couple others, but I'm drawing blank on what they are.
Will you create a topic where we can post them?
Yes, I will create a topic for you to post it. Yes, I'll post some questions for you to go through. I'll go through right now and pick some for 18 and 19. I am not going to give you a kappa before this test. That would be insane. But I will give you a mega kappa to prepare you for the final. So lots of problems for you to practice before the final. Which movies tonight? I said any 2. So I'm not going to decide now that that one's not worth it. So yes. There's a dinner. The only problem I have with anything you pay to attend is that not everybody can take advantage of it. So I have a problem with those, but it's a seminar, right? It's a seminar. I'm not qualifying which ones you can and can't use. So any 2 seminars.
Is it seminars from like last week on out? 'Cause I did like.
Yes, seminars last week are good. Yeah, any 2 seminars. Yep. Somebody asked about the paper. Let me tell you about the paper. Obviously, I am not as adept at grading these as other people, so I'm still working on it. And so I will get them done as quickly as I can. Please be patient with me. The average is still running between 85 and 90. So that's what I've been saying all along, is that they'd end up being there. So that will happen. I'm just trying to make sure that I don't abuse anybody too much. So when I start abusing the paper, I stop. There was another question. Yes, you may still do community service. As a matter of fact, I just got an email today. Relay for Life, Friday and Saturday, needs 15 to 20 volunteers an hour. You do need to write a reflection on your participation on that. And so if you want to volunteer for Relay for Life, stop in the office that's just past, what are they now, the Jolly Scholar in Twing, the whatever office that is, and see Colleen, and she can help you out. I'm sorry? Student activities and leadership, thank you. Yes, if you're participating, I'll take it, I will accept that. Did I get your email? About which event? Yes, I did get the Cedar Players event. That's Friday and Saturday. Do you have all the performers already? Okay, so it's just attending as observers now. I'll post it to Blackboard. There's an arts event on Friday and Saturday, right? Cedar Players. Yes. Yes, you can't just show up and say I was there. You have to tell me what you got out of it.
Do you want us to write a reflection for trying out for the Hudson Relays?
No, you don't have to write a reflection for trying out for the Hudson Relays unless you lost your lunch. Then I want to hear about it. If you tried out for the Hudson Relays, they're supposed to give me a spreadsheet with all your names.
What if you show prospective students around campus?
Nope, you can't show prospective students around campus. That people get paid to do.
What if you're not getting paid though?
Then you're doing it out of the goodness of your heart, and we appreciate that. All right, anything else? Who was it who asked me to do that? Where is Alexis? It's Monday, she's not here. Yes, ask her to remind me. Have her send me an email, and I'll post it to Blackboard and send it out when I remind you of your meeting rooms. Which reminds me, there's an exam on Thursday, chapters 18 and 19. Suggested problems from chapter 19. As I look through here, I would say that the following problems are good ones. Got an extra pen so I can remember what I said. I don't like that one. 12 and 16. 19. I don't have chapter 18 in front of me right now. Actually, you're not going to see that because the screen's not down. Go ahead, please, Jess. 12 and 16, I especially like 16. Oh, you can't see it. It's right there. It's predict whether the following reactions would occur spontaneously or not. Yeah, I will post these to Blackboard. That's why I'm circling them, so I remember what I said. 22 and 24 are nice because they get you delta G and K from E zeros. Effective concentration, 30 and 32. I have to look through these review questions. There's some nice ones that are talked about in terms of short answer questions that would be good. I'm not big on electrolysis. We're not going to worry about electrolysis. So that's all of these questions. I'm sorry? No, they won't be on the test. I mean, it's Q equals I times T. It's a very simple calculation, but I'm not going to worry about it. This actually is one of those wonderful problems, 62. We'll talk about it. The oxidation of 25 mils of a solution containing iron requires 26 mils of 0.25 molar potassium dichromate in acidic solution. Balance the following equation and calculate the molar concentration of iron. So it's a titration problem with oxidation reduction. Don't worry about the fact that it's an oxidation reduction. It's just a titration problem with a balanced equation that happened to be an oxidation reduction equation. So it's not too bad. This is also a fun one, number 64. A sample of iron ore weighing 0.2792 grams was dissolved in excess dilute acid. All the iron was converted to iron 2, and the solution required this much KMNO4 for oxidation. Calculate the percent by mass. These are some of the ones you might want to ask me about Wednesday in class or at your help session. Here's another one, 66. That's an oxidation reduction and a titration. '70 is how to make a pH meter.
Glass electrode and reference steam chapter. Or bond. Yeah, for that I had done the same, used buffers.
You know what? 76, that's probably enough from chapter 19. If you look at 76, remember we talked about solubility rules for chlorides? All chlorides are soluble except silver, mercury, and it was a specific form of mercury, mercury 1. And mercury 1, remember, has the formula Hg2, 2+. This problem explains to you how you know it's Hg2, 2+. And so it's an interesting problem because it helps to show you how you can use this to define something we've already observed. I like 76 for that reason. That's the kind of thing that I look for, is the kind of question that's going to make you go back to some of the other things we've done. The other thing I'll tell you is that there is probably going to be a photograph on this test. I have to test it, but the photograph will be posted so everybody can see it. So that means I have to load it onto the computers in each of the rooms. And you will have a short essay question about that photograph. So just to whet your appetite a little bit. Something I was playing with this weekend, I said, oh, this would be a great exam question. So, and then no, it's not my computer, although I was playing with the computer quite a bit this weekend. Questions? That should be enough to keep you busy. What's the extent to which you need to know about batteries? How many days have we talked about batteries? What do you think the extent we need to talk about, what you should know about batteries is? I would read the chapter, understand it. No, I'm not going to ask you, tell me what the equation is for this battery. But I will ask you to explain why is it that this battery, this 9-volt battery, we've said is actually 6 1.5-volt batteries. A lead storage battery is really just 6 2-volt batteries. The car battery is 6 2-volt batteries. Understand why you would do different things like that, so that, I'm done with that, thanks. So for example, what I did in class the other day was if I take this table of standard half-cell potentials, and you will be given one of these, if we go to the two extremes, so I did this once already, I'll do it once more. If I take the two extremes on this table, and if we think about the periodic table, these are the two extremes of elements on the periodic table. Lithium is going to give up its electrons. Lithium metal loses electrons very easily, and we can tell that because look at the size of that cell potential. It's 3.05 volts negative, written as a reduction. If you turn it around, you're going to generate a positive 3 volts. We like positive voltages. We don't like negative voltages. Negative voltages means we have to put energy in. The purpose of a cell is to get energy out. So if I reverse that reaction, lithium gives up its electrons. Fluorine, we know, is very electronegative. It wants electrons. It will pick them up. So if I reverse that lithium reaction and leave the other one the way it is, whoops, I did that wrong. The maximum voltage that I can get from any elements on the periodic table is about 6 volts. So if I've got a car battery that's 12 volts, there's absolutely no way that I can take a single cell, and when I use the phrase battery, I should be a little more careful. Battery is a collection of cells. It may only be one cell, but it's more likely more than one. So if I have a single electrochemical cell that includes lithium metal and fluorine gas, I could generate 6 volts of potential. If I want 12 volts, I would need 2 of those, and I'd have to chain them in series. That would be the only way to get 12 volts if I was using this reaction. And there's no way to take a single reaction, so I can't have a single cell battery to generate 12 volts. Emma? Okay. Let me come back to that. I think I know where you're getting. No, you don't always make it positive. First of all, that's the first order of business. And I'll show you an example of where that's true. And so the point of a car battery is if I want to generate 12 volts, I'm going to have to chain together multiple electrochemical cells. That's one of those things about batteries we've talked about several times that I hope you understand. And when I take the 9-volt battery out of here, there's absolutely no way to take a single electrochemical cell and make it into a 9-volt battery. I have to chain together 6 1.5-volt cells to make 9 volts. So there's actually 6 electrochemical cells in here connected in series. And the 1.5 volts, this is what I would not ask you, is what is the reaction that does that? I'm not going to ask you to memorize that. You know I'm not big on memorization anyway. It's understanding. I would tell you what the 1.5 volts are for this. It's manganese dioxide with zinc. What happens in this battery is exactly the same as what happens in a AAA or a AA. But then I might ask you what's the advantage of this battery over a AA or a AAA battery? What is the advantage? Why would you want this in your electrical device instead of a 1.5 or a AA or AAA? Well, that's the question. Do you think this weighs more than a AA or AAA? Yeah, it does. So there's more stuff in here. But they're connected in series now. Well, it would be like 6 AA's, but I think if you weighed that, do you think it's equal to the weight of 6 AA batteries? Is there really 6 times as much stuff in there? No, this one has 6 small little 1.5 volts. And so the reason why we have this package is we put it into devices that need a large voltage. They don't need a large current. How do you get a large current? You get a large current by having lots of stuff. So the bigger the battery for the same voltage gives you a higher current. That was that equation that I said I don't care a whole lot about. Charge equals current times time. So if I want a large charge or current here, I need a large charge. Well, I get a large charge by having lots of electrons. The charge is equal to the Faraday. The Faraday is the charge per mole of electrons. 1 mole of electrons has 96,485 coulombs of charge. And so if I want a high current, I need lots of electrons, and I get lots of electrons by having lots of stuff. This doesn't have a lot of stuff. Instead, it's got 6 small amounts, so it's got a high voltage. And so this battery goes into a piece of equipment that requires a high voltage, but not a large current flow. Whereas a D-cell battery, the great big one that's 1.5 volts, is going to have a lot more stuff in it than this does. It has a larger charge. And so you're going to generate more current out of that. And so you use those in big flashlights. If a police officer whips out the flashlight, they used to have about 6 of those D-cell batteries in them. So it's just like this. It's 9 volts, but guess what? It's 9 volts and there's a lot of stuff in there. So it generates a huge amount of current, and so it's a very bright light. It lasts a long time and it's bright. Nowadays, they use LEDs in the light bulbs. If you buy a mag light, they have little LEDs in them. Those LEDs don't require a lot of voltage anymore. So you can put AAA batteries in them, and they'll work just great. So I want you to know about charge and size. Packaging makes a difference too, right? I mean, the fact that this is a nice, convenient size helps. What is it about the cell phone batteries that makes them so advantageous? They're lithium-ion batteries, or they're nickel-cadmium batteries. They're solid state. They just have solids in them for the most part. They're rechargeable. They're reusable. What's the problems with them? They use heavy metals. Cadmium's a heavy metal. Look where it is on the periodic table, back behind us in the back there. It's a heavy metal. Heavy metals are not good things. They're not bad, but they're not good. And so you have to dispose of those things. That's why they say to recycle them. You shouldn't throw your cell phone battery away. Mercury batteries that go in hearing aids. Mercury batteries are very small. But that small size you need that small size, so it's unobtrusive. But then once you've got it in there, you want a relatively high current, and so voltage, and so mercury has a huge voltage. So there's advantages. So think about those things as you're talking about the battery. And yeah, you've guessed what the picture's all about. Yeah, that was pretty obvious, right? I opened the hood of my car and I took a picture of the car battery, maybe. Wouldn't that be cool if I did that? No, I didn't do that. But I do have a nice picture for you. The other thing, though, is we want to talk about concentration a little bit. I'm not going to do this one. Skip anything that talks about current times time. Although, what's interesting about that current times time is that's the way that you would take a cheap piece of metal like aluminum is now a cheap piece of metal, and I can silver plate it. I can coat it with silver by forcing the silver ions with current to coat the outside of the metal. And so that's how you chrome plate a bumper. And you get a very thin layer of chrome over a steel bumper. All you've done is the way they used to do this is they had these big vats filled with dissolved chrome. So there's chrome ions floating around in this vat. And then they would take a steel bumper that has an electrode on it, and they'd put a current onto it. Just plug it into the wall socket. You definitely didn't want to touch these. But they'd take that thing and they'd dip it into the chrome bath and pull it out, and because it was charged when they put it in, the chrome ions would be attracted to the charge. They'd coat chrome metal on the outside of this bumper, and you'd have a nice shiny bumper with a real thin layer of chrome, and it was adhered very strongly. Bumpers on a 50 Chevy, that chrome sticks. Around about the late 60s, they started to paint the chrome paint onto it so you can peel that off. It doesn't stick as well. The real problem why they don't chrome bumpers anymore is chrome, if it's in a +6 oxidation state, is really nasty stuff. It causes cancer like you wouldn't believe. And so all those people in the auto industry who were in the chrome baths ended up getting cancer. And so they stopped putting chrome on cars as well. It got to be too expensive too. But if I let's try a simple one. Actually, you would ask me a question about changing the sign, Emma. Let me show you that one. I'm going to randomly pick 2 half-cell potentials off of the sheet here. Just pick 2 of them. And the two that I'm going to pick are, let's take lead plus 2 electrons negative 0.13 volts, and actually this one's going to be nice. All right, those are my two reactions. And the question I'm going to ask is, how would you combine those two reactions to get a spontaneous chemical reaction? Okay? You've got two reduction potentials there. Both of them have electrons on the left side. You've got to make one an oxidation, so you're going to have to reverse one of them. If you look at the equation in the book says E cathode minus E anode, again, I don't like that equation. It's not a bad equation. It's just easy to mess it up. I'm going to have to reverse one of these. Pick one. You could pick either one and then add them together, or you could pick the right one and add them together, but we could pick either one. So I'm just going to reverse the first reaction, which it ends up as the right one. So when I reverse that reaction, the voltage becomes positive. You just change the sign. I've got to add these two reactions together in such a way that the number of electrons cancels. So by inspection, I can see I need to multiply the first one by 2 and the second one by 3. So I've got 6 electrons on both sides of the arrow now. And now I'm going to add them together. If I've done my job right, I won't have to worry about electrons. And so the cell voltage for that now combined reaction is 1.09 volts. Hopefully, if I give you any set of reactions, one way I might ask it is pick any two reactions to generate at least 1.2 volts of electricity, of voltage. So you could pick any reactions that you want as long as you get 1.2. We want it to be positive. We always want our half cell or our cell reactions to have a positive voltage. And the reason for that is that the change in free energy is equal to negative n, number of moles of electrons, times the Faraday, which is in coulombs per mole, times E0. And so in order to get a negative delta G, which is what we want for a spontaneous chemical reaction, we need a positive cell voltage. Mustafa? Did I forget to multiply by 2? You mean I might have balanced the equation wrong when I started? Up here I need 2 H2Os. So that means I need a 4 here. Does that balance now? Yeah, that looks better. Okay? Here's a question I might ask you. Does lead dissolve in nitric acid? If I put lead into nitric acid, will it dissolve? Why? Just because it sounds like an easy answer? All nitrates are soluble, but does lead dissolve in nitric acid is the question. If I put lead into water, will it dissolve? No. Can you use electrochemistry to answer that question? Will lead dissolve in nitric acid? What do I have? I have HNO3 up there, right? I've got nitrate ions and H plus ions. That sounds like nitric acid to me. So if I put lead solid into nitric acid, what do I get? Lead ions. Yeah, it dissolves. And how do I know it happens? Because E0 is greater than 0. It's a spontaneous reaction. Do you think the equilibrium constant for this reaction is very large or very small? I've heard a large and a small. Well, how are we going to get it? Well, we know delta G is negative NFE. What else do we know delta G is equal to? RT natural log of K. We got that last chapter. Well, that must mean that I can use this to measure this. So how do we rearrange this? Well, we get E0 equals minus RT over NF. The minus sign is gone, actually. Natural log of K. So K the inverse operation of natural log is e to the x. If I do all my algebra, I think I did that right. K is going to be equal to the number of moles of electrons times the Faraday divided by R, which is 8.314 joules per mole Kelvin, divided by the temperature, times E0. Well, E0 is only 1 volt. So we've got e to the first. That's not a very big number. What's RT over NF equal to? Or NF over RT, excuse me. Well, let's see. For this reaction, what's N? 6. There's 6 moles of electrons. What's F? (96,485 moles of coulombs per mole). R, 8.314 joules per mole K. T, we'll say at 298 K. The units on this whole quantity should be what? Anybody know? Nothing. There should be no units. So this has units of voltage. Over here, what do we have? We've got Kelvin canceling. We've got coulombs and joules in here that don't get rid of. Everything else sticks around. The moles of electrons work out to cancel out. So we're left with coulombs per joule. Coulombs times voltage equals joules. So the units do work out. It's a unitless number. But anybody know what that number is yet? 6 times 100,000 is 600,000. 8 times 300 is 2,400. 100,000 divided by 2,400? How much? 24-ish. So we get e to the 24th. Is that all? No, I think it's bigger than that. That's better. 600,000 divided by 2,400. 1, 2, 3, 1, 2, 3. It looks like about 300 or 250. So the answer to this thing is K is e to the 250th. Try doing that on your calculator. Do I have to multiply it by 1.09? Yeah, we would have to multiply it by 1.09 for approximate value. But e to the 250th, try doing that on your calculator. Will it work? No, it won't, because it's about 10 to the 120th. Your calculator won't give you a power greater than 10 to the 99th. That's a huge number. But look at the voltage. This cell potential of 1.1 volts, which doesn't sound very big. I mean, if this is a 1.5 volt battery, that's less voltage than in this battery. And yet look at the size of that equilibrium constant. It's monstrous. Cell voltages of really small values correspond to huge values of delta of K. And so you can use cell voltages to measure K because we can measure voltages very accurately. So when we start talking about millivolts, 10 to the minus 3 volts, K values are still going to be on the order of e to the 10th, which is still a very large number. And so when you look at this, it's perfectly natural to say, oh, that's not very much. But in terms of the chemistry of this reaction, it's a huge number. That tells me that when lead is put into nitric acid, guess what? The lead dissolves. And you're going to get lots of product. Does copper react with nitric acid? Well, let's take the same half reaction for lead, or excuse me, for nitrate, but let's put the copper ion reaction in here. So we've got nitrate. And now let's see what the reaction is for copper. Let's do copper solid to copper 2. Now that I'm comfortable enough with these, I'm actually going to just reverse it in my head. So when I reverse it in my head, on here it says 0.40 volts. So E0, since I've churned it around, will be equal to that. I don't even need to worry about getting the balanced equation. This would be copper metal being put into nitric acid. It's got a positive cell potential. Does nitric acid dissolve copper? Yeah, it does. We've got a positive cell potential. It's a spontaneous reaction. So nitric acid will dissolve copper. Will hydrochloric acid dissolve copper? Where's that table? There is actually a table in there that talks about whether or not acids will react with certain metals. So the question is, can we take copper, 0.40 volts. Okay? Copper to form copper plus 2 ions. And the reason why I picked plus 2 is because it's the more common one. And now, will it dissolve in hydrochloric acid? Well, what's hydrochloric acid? It's H plus and Cl minus. So I'm going to look on here and I find out that at 0 volts, 2H plus 2 electrons to make hydrogen gas. No, I've been using 0.4. I'm going to stay with that. Don't want to change it in the middle. That's my dyslexia coming through. So when I add these two reactions together, copper doesn't react with H plus in the hydrochloric acid, at least not spontaneously. So you can take copper and put it into HCl and nothing will happen. But what about with the chloride ion? So I have to look on this table to see if there's a chloride ion on here. Chlorine, here we go. What do I need? I need this reaction. Well, actually, let's do it the right way. Chloride ions I have it backwards, don't I? Yeah, that's all right. So it doesn't react with H+. Does it react with chloride ions? E0 for this is negative 1.36 volts. Will copper metal react with chloride ions? Will they? If I react copper metal, copper solid, with Cl minus, do I have both an oxidation and a reduction? No, I have two reductions. Excuse me, two oxidations. So will copper metal react with chloride ions? No, it won't. But we do know that copper ions, if there's chloride ions around, will do what? All chlorides are soluble except silver, mercury, lead, and one of the coppers. That's the one we don't usually talk about, but one of the coppers is. So if I reverse one of these reactions, if I want to get a spontaneous reaction out of this, which of these two reactions should I reverse? The second one. So if I reverse the second reaction, E0 equals 1.36 volts, and I take copper metal, what this tells me is that copper metal and chlorine gas are not a good combination. Chlorine will dissolve copper. So if you're designing a swimming pool, don't use copper pipes to put the chlorine gas in the pool. It's not a good idea. How did I find the difference between the reacting with HCl or reacting with chlorine gas? The way that I did that is the question I'm asking is, does copper react with HCl? Well, I know that one of the half reactions I have to use is this one. If there's a reaction, I'm talking about copper metal. I should be more explicit. Does copper metal react with HCl? I have to have that reaction, copper to form copper ions. I don't know if it's copper 1 or copper 2 yet. I picked copper 2 because it's the more common ion. I'd have to do this reaction again with copper 1 ions. And then if I've got HCl, because it's a strong acid, I know I've got H plus and Cl minus. So one reaction that I can find on my table of reduction potentials is H plus plus a couple of electrons to give me hydrogen gas. I don't even have to look that one up. That's one that I know the cell voltage of. When I looked up the copper, again, it was negative 0.40 volts. Okay. Refresh our memories. Now when I combine these two together, the cell voltage will be negative, so it's not spontaneous. So copper does not react with H+. That's what that tells me. Does copper react with chloride ions? Again, I look on that table of reduction potentials. Can I reduce chloride any lower? Can I make Cl minus 2? No, I can't. Chlorine is minus 1. That's as low as it goes. Remember, it's in the 7th column of the periodic table. Its possible oxidation numbers are +7 through -1. And so it can't be -2. So chloride ion can't be reduced anymore. It can only be oxidized. Well, if it can only be oxidized, we want to know if this can be oxidized. So I can't have two oxidations. So no, copper metal does not react with hydrogen ions, and it does not react with chloride ions if I make copper 2 ions. What if I make copper 1 ions? I do exactly the same thing, except now I'm going to look up what's the half cell potential when I take copper metal and make copper 1 ions. So I look through my list here. How do I start reacting chlorine with copper? How do you mean, how do I start reacting chlorine with? Oh. How is this one different from that one? Because what I just did over there and what I did over here were two slightly different things. Over there, what I said was, and I didn't finish it because I used logic to finish it, is I said, okay, I'm going to oxidize my copper metal to copper ions. So that means I need a reduction to go with it. If I reduce hydrogen ions to make hydrogen gas, the cell potential is 0 volts. And when I add these two together, I get negative voltage, so that can't happen. That makes sense, right? Okay, so I can't react H plus with copper metal. All right, so if I'm going to oxidize copper metal, could I reduce it with chloride ions? In other words, could I oxidize it with chloride ions? Could chloride ions be reduced further? And the answer is no, they can't. You can't make Cl minus 2. So there's no way to make a reduction of chloride to couple with the oxidation of copper. So that's how I did that one. Over here, I did it the other way. I said, okay, if I know that the cell potential for copper is negative 0.40 volts, and this one's a negative 1.36 volts, how would I combine the two of them to get a spontaneous reaction? And the only way I can combine the two of them is to take copper metal and react it with chlorine gas, but the question said, does copper metal react with HCl? Not with chlorine gas, with HCl. So I don't have chlorine gas. I've got chloride ions. So I just answered it two slightly different ways to get to the same answer, right? Try it with copper plus 1. Can you oxidize copper metal to copper plus 1 using HCl? I'll see you on Wednesday.